All right, as the last few guests settle down and sign in, let's go ahead and get this Stillwell Memorial Lecture started. It's my pleasure to welcome you to the second Stillwell Memorial Lecture, named in honor of H.S. Stillwell, who was the founder of the Aerospace Engineering Department, then Aeronautical Engineering back in 1944, and this is its 75th anniversary. And as part of that anniversary, we have several seminal speakers. Dr. Graham Candler from the University of Minnesota is our guest today. Stillwell was influential in the design of one of the first ramjet-powered missiles, somewhat relevant for today's topic. And equally important, he's very highly respected for his contributions to engineering education, of which he had a long commitment to. Because Professor Stillwell had such an impact, obviously, on this department by its founding, but also for his contributions to it, in honor of your visit, we have this gift, which is to represent the cornerstone with which Stillwell...
It's heavy.
It is heavy. Don't throw it at anybody.
Thank you.
And if you want us to ship it as opposed to security, we can talk later. But it's with great gratitude that we give you this in honor of this, okay?
Thank you very much.
All right, so now that that's out of the way, let me introduce the reason why we're all here, which is Professor Graham Candler. Professor Candler is very well known in the field of hypersonics, of which the topic of his talk you can judge. He's also the Russell Penrose and McKnight Presidential Chair of Aerospace Engineering and Mechanics at the University of Minnesota. He received his PhD in Aeronautics and Astronautics from Stanford University with Bob McCormick, and since then has been a mainstay in the development of CFD methods for hypersonic and reentry flights. He has a very large number of contributions to the community. Some of them are bundled into codes with which he is synonymous. And I'm thinking of Dept, which he helped at least orchestrate, if not write any code to. And then more recently, Stable, which is a boundary layer stability code, and US3D, which is the unstructured version of Dept and continues to be one of the major CFD codes in hypersonics and reentry systems. Dr. Candler has published several hundred articles, conference papers, and books. He has received the Dryden Lectureship from the AAA in 2018, the Fluid Dynamics Award from the AAA in 2012, the Thermal Physics Award from AAA in 2007, and he's a fellow of the AAA as of 2007, so 12 years ago. And he continues to be one of the moving forces in hypersonics in the United States. And with great pleasure, I introduce you to Dr. Graham Candler.
Thank you. Thank you.
Take my notes.
Okay, glad that's over with. Thanks a lot. Thanks for the invitation and the chance to visit Illinois. I always have a great time when I'm here. It's fun to see people that I've known for a long, long time and meet. Kelly was one of my undergraduates at Minnesota a long time ago. Well, not that long ago, but anyway, so it's great to be here. Thank you very much. And let's get going. Okay, so I'm going to tell you about a few things that we've been working on. And that's this flight experiment. I have a 3D printed image of it here, so you can see it in 3 dimensions if you like. This is going to fly on a sounding rocket in May of 2020. And so what I thought I would do is tell you sort of the background of this thing. And to start with that, since I don't think everyone in the room is a hypersonic boundary layer transition expert, I thought I'd tell you a little bit about the underlying physics that happens in a flow field like this, and then what we've been doing to try to understand the flow field, and really, and to a large degree, this has been a very exciting project because it's really pushed the CFD capabilities to a whole nother level with the goal of predicting what's actually going to happen in flight. So BOLT, boundary layer transition, flight experiment is actually sort of the third in a progression of experiments, boundary layer transition experiments flown on sounding rockets. And there were 2 earlier flight experiments, a blunt cone, HiFire 1, and then HiFire 5, which was a blunt cone that was squished by a factor of 2, so it's elliptical in cross section. And then this configuration, this geometry here now, BOLT. And the big deal here is that it has this much more complicated shape. It's got a concave surface, and it has these swept leading edges. So it's definitely not a flight article. It's not something that anyone would build and fly as a practical application of hypersonics, but it has some of the interesting physics in it, and that's really what motivated the choice of this. So here's what's going to happen is that this is what it looks like on the stack. Physically, this geometry is about 86 centimeters long, not quite 3 feet long, and it's going to fly on a 2-stage sounding rocket. It will, if all goes well, it will make measurements on ascent while attached to the second stage, going up at about Mach 5.25, and then it'll turn over, hopefully again. That's a tricky maneuver. Get it back, pointed back down to hopefully low angle of attack, and it will then enter the atmosphere at Mach 7.5. So there are really 2 sets of experiments that will be done, ascent and descent. And so how did this geometry come to be? Well, we started actually with kind of a Play-Doh model of this from the program manager, Yvette Leva at AFOSR. And we had spent a lot of time on the phone trying to figure out what it was that she wanted us to do. And so she sent us this thing that to me looks a whole lot like a tongue. I don't think that was her intention. And then AFRL had this idea of sort of this kind of wave rider derived configuration. And then we have another idea where we sort of wanted to separate the two surfaces, but this looked kind of too much like HiFire 5, the convex shape. So we sort of mashed all of these together, and we ended up with this geometry. And when I say we, that's actually my student, John Tomei, did all of this work. He was the CAD expert who came up with this. And basically, in the process of doing this, we were sort of running CFD in real time and trying to see what the flow field would look like on this geometry. So again, key things are swept leading edges and this concave wave rider-like configuration. So that's what we want to understand. Okay, so why is it that particular geometry is of interest? Well, of course, it's all about boundary layer transition. This is a boundary layer transition experiment, hence the name BOLT, right? And so here's just some examples of images of boundary layer transition. You can see on this is a projectile. It's only Mach 3.5, so it isn't really hypersonic, but it's flown in a ballistic range with very, very low disturbance levels in the ballistic range. And you can see these blobs of turbulence breaking out. You can see shock waves being shed off of those. And on the lower surface, the lower image, part of the image, you can see actually the transition occurs fairly far upstream. You see this boundary layer turbulent boundary layer forming very thick. And you see all this noise radiated off the boundary layer. Lots and lots of physics going on. Over here, this was actually a flight experiment. Unintentional, actually there was an intentional flight experiment, but the really interesting thing is unintentional. On STS-119, Tom Horvath from NASA Langley and his team made measurements of the shuttle. This is about Mach 8.5 condition during reentry using an IR telescope pointed out the side of a P3 Orion. And you can see here that what happened is that the nose gear door wasn't fully closed, and that door sticking up produced this whole huge region of turbulent flow. So these colors represent surface temperature, and you see that this part where there wasn't transition is cold, and this side is hot, and of course that's what boundary layer transition does, is it increases the heat transfer rate and therefore the surface temperature. And you can see very, very high heating in where the bow shock comes and impinges kind of on the leading edge here. Very, very dangerous condition, actually. Could have caused failure of the TPS, of the thermal protection system. Here's another nice cone at angle of attack that shows a different form of transition, so-called cross-flow transition. Here's a boundary layer, a laminar boundary layer being hit by a shock wave, and that causes obviously separation and transition to turbulence and transition turbulent flow downstream. This is the HiFire 5 geometry, looking down on that 2-to-1 elliptic cone, and you see this is temperature-sensitive paint, and you see these wedges of high temperature and therefore therefore turbulent flow, And you can see these really streaky structure upstream of these that then break down and go turbulent. And some other structure probably unrelated on the center line. So you can see different mechanisms of transition. Here it's because of the crossflow. Here it's another form potentially of crossflow. This might be a different mechanism. This is due to a roughness element that causes transition, and this is obviously due to shock impingement. So these are the kinds of problems we work on in hypersonics, and we want to understand, how much was the door sticking out in order to trip the boundary layer? Why did it trip at Mach 8.5 but not higher, et cetera? And we want to be able to predict these flows. So here's how we think about the transition process. And this is a diagram from Morkoven, and this is kind of the way, if you haven't had a boundary layer stability class, this is kind of one of the ways that this is taught. And basically, you have some environmental disturbances upstream. That might be noise in a wind tunnel. It might be particulates in the flow field. It might be turbulence in the flow field. It might be roughness on the surface, something. And then, so that sort of forces the flow. The boundary layer and the flow field has some kind of receptivity that it absorbs those disturbances. And then those either go through so-called eigenmode or modal growth, or through some kind of other kind of more complicated process called transient growth, which then cause secondary instabilities and modal interactions, which then causes breakdown and transition to turbulence. Sometimes when you have a very high disturbance level, you can have bypass, and I guess that the shuttle example would be a so-called bypass, where the nose gear door is so large that it produces a disturbance that just doesn't even really result in modal growth, and it just goes straight to basically nonlinearity and breakdown. So, another way to look at that is in the sort of, this is a low-speed picture, but kind of canonical from undergraduate textbook, but this is sort of saying the same thing, that there is some primary instability that causes a secondary instability, and then those instabilities interact and you form turbulent spots and you break down. And so, this process is what we're trying to understand. Here's a hypersonic example. This is the HiFire 1 cone with, here's the CAD model of it with all the sensors on it. And these are several different runs in the Lens 2 shock tunnel at Kubrick. And you see that there's laminar flow, then there's transition, sudden heat transfer rate rise, and then turbulent flow. And there's roughly, in this case, a factor of 3 or so increase in heat flux. This can be larger. It can be as much as 8, a factor of 8. So, we need to understand this in order to design flight articles. So every particular hypersonic flow field is going to have some mechanism that produces transition. And one of those, probably one of the most important transition mechanisms, is so-called second mode. And this is from a very nice paper by Sasha Fedorov. And basically what he's showing here is that the second mode disturbance is because the boundary layer acts like an acoustic waveguide. And acoustic rays reflect back and forth between the wall and the sonic line, and they can absorb energy from the flow field. This is seen here from results from Stuart Lawrence in the ADC Tunnel 9 facility Schlieren images, and you see these very characteristic what's known as rope waves in the literature, because this looks sort of like a rope. This is an old DNS now from one of my students, also showing density fluctuations in the flow field that are characteristic of this second mode instability. And really what's happening is the boundary layer, it's this narrow region that supports the instability, and this is noise that's radiated off of that instability. I showed another example. This is crossflow, and I showed this cone before. And this is a result of, so this is a cone at angle of attack as an example, but basically it's because the boundary layer, in some cases the boundary layer is three-dimensional and it has an inflection point. And you can see that really clearly here because What's plotted on in this image is the black lines are near surface streamlines, and the red lines are boundary layer edge streamlines. And you can imagine now, you can see that the near surface streamlines respond to the pressure gradient, the high pressure on the wind side and low pressure on the leeward side. So they zoom around the side, but the boundary layer edge doesn't know about the boundary layer very much, and so they just sort of zoom downstream, and you get this inflection or you get this kind of three-dimensional boundary layer, and that boundary layer often supports an inflection point, which is invisibly unstable. And then you get these kind of cross-flow instabilities, and that's actually activated typically by some kind of surface roughness is sort of the expectation and the understanding in the literature. Measurements have been made of these. This is temperature-sensitive paint data from Purdue Quiet Tunnel, and we get quantitative comparison between DSMC and CFD. Roughness is also really, really important, and that's very much an open question in our field, is how rough is rough? And how much roughness do you have to have in order to cause boundary layer to transition? So we separate this into kind of two types: distributed roughness and discrete roughness. And that discrete roughness is obvious what it is. It's something like the nose gear door on the STS-119. Distributed roughness, there's a finite, perfect level of, you can only machine the surface and polish the surface to some level. Surface can be ablated, for example. There could be a small, there could be just small imperfections in the surface. And this is another crossflow case. This is the HiFire 5, and this is an experiment on that. And both of these actually agree with each other very well computationally and experimentally. These disturbances were actually seeded by roughness. They are very, very dependent on micron scale roughness on the surface of this wind tunnel scale model. So roughness is really important and can set off these instabilities in the boundary layer. And this, of course, is a discrete roughness. There's a cylindrical object sticking out of the surface, and this is what happens in the boundary layer downstream. Okay, so that's kind of a warm-up. How do we predict this? Well, until about 15 years ago or so, everything was done with correlations. And the favorite correlation was this right here, that the Reynolds number based on the momentum thickness at transition divided by the edge Mach number is a constant. And so I just showed you these really complicated physics, and it seems a little bit ludicrous that such a correlation could work, right? So if you apply that to the HiFire 1 cone, and you do some measurements at NASA Langley and at Kubrick, and you use this transition criterion where 150 is the TRL 4 or 5 or 6, depending on who you talk to in the old days, number for cones, and now you plot predicted transition Reynolds number versus measured. And so you'd like the black line that you predict something, you measure the same thing. Now you put your data on there, and you see it's almost a perfect anti-correlation. So this was, as I said, this was the standard until we started understanding better these mechanisms that we were just talking about. So now we do mechanism-based stability and transition prediction, and that's actually really quite easy to understand. There are details that are challenging, but conceptually it's very easy. You simply linearize the Navier-Stokes equations about some laminar base flow. So you do a very high quality simulation of a base state, a simple flow field, your flow field of interest, and then basically you solve some kind of eigenvalue problem for the disturbances. And in particular, the best way to do this is with parabolized stability equations. And that's sort of illustrated here is that you have some disturbance field that you represent this way with a shape function and some streamwise growing component and a wave frequency component. And you integrate those disturbances downstream, basically solving an eigenvalue problem in each location. And that allows you then to compute the disturbance growth rates. And then in order to do a prediction, we estimate the transition based on a critical relative amplitude. Okay, so what is that? We call that the N factor. That N factor is a function of the frequency and the location where you are. And it's simply the ratio of the amplitude of that particular omega disturbance relative to its initial disturbance. This is a linear problem, so we don't know anything about absolute amplitudes. All we know is about relative amplitudes. And that's then the integral of the growth rate along the surface from the initial state to the state of interest. And so then what we do is we say, well, we're going to use a critical N factor, which depending on the conditions, we might pick to say 10. And that means then that when the amplitude has grown relative to the initial amplitude of this factor, we have transition. And so, an analysis like that is shown here. So this is the high fire 1 cone, and this is the second mode disturbance. And basically what you can see here is distance and frequency of disturbances. And what's plotted are all of the disturbances in this little banana-shaped region are where the boundary layer is tuned to acoustic disturbances. And this negative alpha I is the growth rate, and that means that in this region of space and frequency, the boundary layer is unstable to disturbances. And that's because the boundary layer speed of sound and thickness is tuned to frequencies like here near the nose of like 600 kilohertz, and then as you go further back, maybe 200 kilohertz. Boundary layer is getting thicker. It supports longer wavelength, lower frequency disturbances. Again, thinking of it as a waveguide, for example. So then what you can do is you can take this analysis, and now you can plot this in a different way, plot the N factor, which remember is sort of the log of the relative amplitude or the integral of the growth rate, versus distance, and you can take each disturbance and track it. You can see this red disturbance goes up, the boundary layer is tuned to that particular frequency, and then it decays because the boundary layer is detuned. So now you put a whole envelope of these things, do a ton of calculations, and you get this green curve, which is the envelope of the locally most unstable disturbances. And so if you are operating in a facility where you think, or on flight where you think the critical N factor is 10, then you can use this analysis. You say, well, here's my critical N factor is 10. I read off, okay, transition is going to occur at 0.2 something meters. So this is the kind of analysis now that we can do because we have the ability to rapidly and accurately generate these stability diagrams on geometries. And so how does it work? Well, here's our old style anti-correlation. And here for an N factor of 5.5, which I'll explain why we chose that in a moment, but you see this like amazing agreement. This is actually across different Mach numbers, different facilities, different wall to edge temperature differences. I mean, very wide range of conditions here. And you see it really correlates the data very well. That's because that second mode disturbance is actually the mechanism that is causing transition. It's not some thing like this. It's just not, this is just wrong, obviously. Why do we choose N factor, critical N factor of 5.5? Well, the value of N star depends on the free stream disturbance amplitude. So if we're testing in a noisy wind tunnel where there's a lot of noise, the boundary layers on the nozzle are turbulent, they're radiating noise onto the model. There's a large background amplitude. A0 is large. And therefore, you can only tolerate a certain amount of growth before the disturbances get critical and break down and go turbulent. Till they reach an A star, an amplitude, a critical amplitude. So we pick an N star of about 5.5, 6 typically for conventional non-quiet wind tunnels. In flight, it seems like N star is probably more like 15 or so. And that's because in flight, the free stream conditions are very quiescent, there's very low disturbance levels, and therefore the critical amplitude is reached at a higher N factor. So this is still a so-called semi-empirical approach because you have to have some knowledge of of what the critical end factor is. Okay, so then also importantly is that this kind of analysis also predicts frequencies in the boundary layer. Okay, so let's turn to Bolt now, finally. And so here's a wind tunnel measurement of Bolt, and you see this is in Kubrick lens 2 with a temperature-sensitive paint, and you see this, these two lobes of transition. And now we know enough about boundary layer transition, we might say, well, this could be some kind of so-called stationary crossflow, or some kind of crossflow instability like we saw on the HiFire 5 geometry. But really the flow field is actually very complicated. So here we're looking at the nose of the thing, and you see this lifted boundary layer, see distortion in the boundary layer. This is streamwise velocity. And so, yeah, we have this wind tunnel measurement, but this is done in a non-quiet wind tunnel. We don't really understand the mechanism. What is driving these two lobes of transition? Is it a facility effect or not? Is it a background noise effect? Is it this mechanism or is it something else? And so really the kind of big question is, how do we do a stability analysis on this very complicated flow field? And which modes are present? We'd like to characterize our modes. We'd like to know what's going on. Okay, so yeah, okay. My timer on my computer is freaking me out. It says we've been at this for 43 minutes, and I think that's not correct. I hope it's not, because I do have a couple more slides to talk about. Okay, so what we do, we're CFD people. And so how do we do CFD of this thing? And what is novel about what we're doing? Well, we're doing high fidelity CFD solutions. And so high fidelity is one of those words, like, it's really kind of meaningless, right? It's beauty is the eye of the beholder. You got to, it means something to everyone. It's something different to everyone. And actually, so what we're doing more quantitatively is we first of all using a very, very fine grid with very smoothly varying features and very carefully aligned with the bow shock wave. And that sort of is shown here in the nose region. And this is a very small fraction of the number of grid points that are actually used. But there's this complicated and very careful grid design. And the shock wave really lies on one of these grid lines so that very little stair-stepping occurs across the shocks. Then we also use a low dissipation, high order numerical method. And again, low dissipation is an adjective, it's not quantitative. But we can quantify how much dissipation is present, and it turns out to be very low. And then what we do is, that method itself wouldn't run on a problem like this because there would be noise, there would be error generated, instabilities generated at the shock. So we carefully add a very, very, very precise amount of dissipation at the shock wave so as to stabilize the solution. So this is kind of artisanal at this point, but we know how to do this now. And rolling all this together allows us to do very precise CFD of this. And because in order to get anyone in the field to accept anything you do, you have to call it something nice, something cool. So we call this quiet DNS. And it's DNS of the transition process, not DNS of the turbulence. Okay, so just keep that in mind. And we call it quiet because in the same nature as quiet hypersonic wind tunnels. Quiet hypersonic wind tunnels are designed to have laminar boundary layers on the nozzle. They have very low disturbance levels, 2 orders of magnitude lower disturbance levels in the free stream than conventional wind tunnels. And so they call themselves quiet tunnels, quiet wind tunnels. So we thought we'd call our simulations quiet DNS. I'll try to convince you that that's not really too much of a lie, too much marketing. And so another important thing is the numerics, and really this just is to summarize that that if you try to run, this is just a very simple case where a density pulse is propagated through a domain a few times, and standard CFD methods for hypersonics use upwind methods. Those of you who have had your first CFD class might know about this. And And these tend to have very high levels of dissipation. And then these central methods, low dissipation methods, have different features. And what's shown here in the blue is the second order method that has better amplitude prediction. You can see that upwind is way down here. It's just killing the density pulse. Second order does better, but it has horrible dispersive error and trails all this noise behind it. If you use a fourth or sixth order method, you actually have to zoom in, and you can see that especially the sixth order does amazingly well, but even the fourth order has a little bit of trailing dispersive error, but it really does pretty well. So I'm trying to convince you that the methods are actually very important. Okay, so let's do some CFD. We need some CFD in order to do stability analysis. So here's what happens when you start running Bolt with a second order upwind standard CFD method that's in every code, every compressible CFD code. Here's a 6 million element grid on 1/4 of the actual domain, right? So the grid has been mirrored across here, or the solution has been mirrored in order to show the full thing. This is the looking down on the plan view of this thing. So we keep refining the grid, and you see some additional structure coming out. So 40 million shows some stuff going on, some sort of better definition of some of the streaks and features that are present here in the heat flux. And we go to 160 million and 350 million and 520 million, and there's even a change between 350 and half a billion. Like if you look at this streak back here, you see that it's getting a little bit more intense. There's some additional structure in this region. I mean, it's sort of in the eye of the beholder, but there is still a change here. And of course, we can quantify that. Now, if we go to our fourth order low dissipation method, so I copied the half billion upwind method result there, and we start running, so here's 40 million, and then 80 million, and you see actually this result is at least as good as this. And we think that this guy's probably about equivalent to 50 million or so grid. So you're saving a factor of 10 by doing this method. And you can keep refining, and actually the solution doesn't even really change between 80 and 160, and 520 is basically the same. So the second order is not converged even at half a billion, and this is probably converged around 80, maybe 160. So there's a factor of 10. Okay, so now we have this beautiful result. Here's our predicted flow field. We did this prediction before, actually not this one, we did this, 160 million. We did this before any wind tunnel measurements were run, because CFD is a lot easier to do than wind tunnel measurements. And here's what we got. So we replotted this now, the CFD now, on the same color map as was used from experiments. And now you can see that the experiment at Purdue in the Mach 6 quiet tunnel is this back region of the bolt, and you see amazing correspondence here, right? Hopefully you see that. You should be saying, that's awesome. This CFD stuff actually works, right? And in fact, if you look at this, you can see that the experimentalists actually were running at about half a degree side slip. There's a little bit of asymmetry between the upper and the lower half here because of a slight amount of beta. This agrees, remarkably well quantitatively, and also appears in the Texas A&M Mach 6 quiet tunnel. You can see some of the same features here. So interestingly, no one believed this result. Literally, they thought this was just a bunch of noise generated by the CFD until we got this, until Purdue produced this data. So wind tunnels are good for something, right? Just kidding. So those streaks actually come from physics, and pretty interesting physics. And they come from the curved bow shock. There's a kind of nice paper going back to the 60s, but basically there's a derivation that shows for 2D curved shock, you get this vorticity omega generation. And we think that we can relate this back to where the region of strongest curvature is, that then sort of seeds these disturbances that flow downstream and distort the boundary layer and inject a disturbance into the flow field. If the free stream is perfectly steady, then that disturbance is steady, and that's what results. That's what you see in the CFD images. Of course, if the free stream is not steady, then this could be jittering, and those disturbances could be varying. But the streaks actually come from a reason. Okay, so now we have this nice solution, and now what we want to understand is how does that solution, how does the flow field, the CFD flow field, respond to forcing, instabilities? And so what we've done so far, and this is definitely work in progress, is that we have just applied a little strip of normal wall momentum forcing and then integrated in time. So there's this yellow strip here. We put in stochastic white noise at 10 to the minus 6 type of amplitude, so very, very low. And then we just integrate downstream, and we let the flow field respond to that forcing. And the flow field selects particular modes. It responds in particular ways. And you get these 4 types of instabilities that occur on the bolt geometry. So this is clearly a vortical mode that is in that lifted vortical part of the flow field. There's very clearly these are traveling cross-flow modes, and if you play the movie, these worms, the blue and red worms, just happily march downstream. This high-frequency stuff is clearly second mode, and interestingly, you can see that it sort of dies out, detunes from the boundary layer, and then something happens, and then it gets this additional modal information, or modal response that takes place here that has some kind of obliqueness to the flow. So it's some kind of possibly cross-flow type of instability. We don't really know yet. If you look at the surface pressure, you see that's sort of a signature of second mode. You see this very high frequency noise on the surface. It scales very much like expected for second mode, and so we're really very confident that this stuff upstream is second mode, and you can see even some of it propagating downstream. This obviously is at a different frequency, and we'll see that that's crossflow. Okay, so we have this nice flow field. We've done this forcing. Now we want to understand better, and so what we do is apply so-called sparsity promoting dynamic mode decomposition. And I'm not going to be able to go into details of DMD, but basically what that does is you take a series of snapshots in time of your flow field, and then applying direct modal decomposition or dynamic modal decomposition it basically it selects the modes that best represent this set of snapshots that you've taken. And then the sparsity promoting basically ranks the importance of those by some metric, typically an energy metric. And so we're able to pull out the dominant modes from this DNS data. And it's very, very clear that there are dominant modes, and that this is a modal process. So here, for example, is in the vortical disturbance or instability, there are 3 planes here, and you see what the sparsity promoting DMD produces, these types of vortical disturbances. This is the mode that the DMD analysis says is energetically most important. It's about 50% of the total disturbance energy is in this one mode. And so we predict these frequencies, and so then it just so happened that in the experiments there were some coulites on the surface, and it just so happens that coulite number 1 here happened to be on top of the disturbance. And here's the PSD that was measured, and it comes in at 37 kilohertz. And our prediction is that location is 40 kilohertz, so we missed by 3. But here's actually the pressure disturbance mode, and you see the pressure for this particular disturbance sits right on top of the coulite, and that's why you get this big response of that particular transducer. You see a little bit in the red and not much in the blue, and that's just because the red is not quite in the right spot, and the blue is definitely not in the right spot. But, you know, for us in the transition world, this is pretty good comparison. We can also look at the crossflow, and that absolutely agrees. Sorry, mixed mode. Oh, sorry, that's right. Yeah, this agrees with the I got out of sorts here. The crossflow, we do the analysis, and we get these modes, and this has all the properties, the footprint of a crossflow. Mixed mode is actually very interesting. There are basically 3 modes, this plane, that are sort of equally ranked energetically, more or less equally ranked, and they're at 37, 86, and 141 kilohertz. Here's some Coolites, PSD from 3 other Coolites, and you see that this is lighting up at 37 kilohertz, right where we expect this mode, a little bit of action at 90, and then at a higher frequency, which sort of more or less corresponds to this mode. Okay, so our real goal is to predict what's happening in flight, and so that all of the analysis that I just presented was at Purdue Mach 6 conditions, very low free stream disturbance levels, ideal conditions. I showed you that previous image from Kubrick where there's those 2 lobes of very high temperature. That seems like crossflow dominates. Here's some NASA Langley IR thermography and you can see they also show, like at this higher Reynolds number, which isn't very high actually, you see this big lobe of high temperature region and thereby presumably transition. So we're very worried that these noisy wind tunnels, Kubrick and Langley, are producing transition, activating transition that isn't really what's going to happen in flight, because they have this very large noise level. So we really don't know what the role of tunnel noise is. You can't run at high enough Reynolds number in the quiet facility to get transition. So we don't have transition under quiet conditions. And then flight has additional effects that we have to understand, you know, actual roughness of the surface, thermal expansion of different parts, temperature is going to vary. You're not going to fly at perfect alpha equals 0, beta equals 0. But by March 1, we have to come up with a prediction of where transition is going to occur. Which sensor is going to go from laminar to turbulent at what point in the trajectory? So what we're doing now is working to fly Bolt on at least the best guess trajectory and couple it with a thermal response solver and also use estimated free stream disturbance levels and roughness levels in order to attempt to best replicate the actual flight. And this is now something that actually can be done, which is sort of mind-boggling for an old guy like me, where my thesis was done on a grid of 35 by 50 grid points. It's 1,750 grid points, and every one of those was important. This is now flying an unsteady trajectory on a grid of 350 million elements and doing this time-dependent calculation. So it's completely, utterly different than anything we could dream of doing back in the Stone Ages, when we had to chip our code onto a stone block. Anyway, so we're going to fly this thing down this trajectory, and here's just 3 examples. My students like experimenting with different color maps, but these are particularly beautiful, I think. But you can really see the differences in the structure. I mean, the flow field sort of stays the same. These are actually Mach 7 plus, 7.3 or so, as opposed to 6 before. But the biggest difference is in Reynolds number, of course, from 2 million to 5 million to 10 million. You see just very distinct changes in the flow structure. And you know, now we really kind of understand this flow field. We now need to predict, you know, is it going to go turbulent, here due to cross flow? Are these vortices going to interact with each other? What's going to happen? And is it going to be at 5 or 10 or somewhere in between? And remember this one, this looked like you had transition maybe even here, but certainly here at 2.2 million. This is based on length. And that would indicate that this is the kind of the flow field where transition is going to occur, if you believe the Langley data. I don't think that's going to be. I think it's going to be somewhere between 5 and 10, but we don't quite know what yet. Okay, so just a little bit more about the flow features. Really, we're just starting to dig into this and trying to better understand it. So here are the 3 cases, again, with these slices through the domain. And actually, interestingly, this is kind of a zoom of this region, and you see that this lifted region where there's that vortical instability, you see that it does change character somewhat between 2 and 5 million. But you see at 10 million is completely different. And, we don't really know how this is going to drive transition yet, but, we have the tools now in place to start to understand it. Of course, this flow field is higher Reynolds number, thereby less viscous dissipation, larger range of length scales, and this calculation is actually quite challenging. And just to remind you again of the power of the numerics, here's what you get in that region if you run with the low dissipation numerics. You get this black, beautiful spiral, this vortex, which is shown here. And then if you run with the second order upwind on 350 million, you see you get this behavior. You see they're completely different. And that's just because of the inherent dissipation that's in the numerics. And so John Tomei, my student, based on the resolving power of the second order method, he estimates that you would need about 20 billion elements to get the same result as you can get on 350 with low dissipation. So this is absolutely essential in order to be able to do these kinds of calculations. And you should be taken out back and beaten to a pulp if you say, well, I'm just going to do this, right? I mean, they're big enough computers are big enough to do this, but the math, it's so much better to get a good answer with math than with brute force, right? That's why we're here, right? Anyone can do stuff with brute force. It's getting it the best that you can do, right? That's the power of this numerics. Okay, so we're also letting the body heat up, and this is actually quite important, we think. So we're using finite element method. Here's a grid for that using tetrahedra. We have to, of course, match between the very, very fine. This is 400K, 400,000 elements. We have to match the 2 different grids, doing that very carefully so you don't lose energy. And we also exploit the discrepancy in the fluid and time scales. The fluid is very, very fast. It responds very quickly, and the flow field, the solid is slow. And so now we can fly this thing. And what we'll do then is, take snapshots as we go through we'll take flow states as we go through the trajectory. And then at each of those flow states, we'll do an SPDMD analysis to try to isolate the modes as the Reynolds number changes, and therefore to predict transition. You can see here that Bolt is there's actually a non-trivial variation in surface temperature because the nose is made of tungsten, there's a stainless steel region, and then there's an aluminum region, and the different thermal properties result in different temperature distributions. Okay, so this baby is almost ready to fly. Here is the built up that I showed earlier. It's under instrumentation. 340 sensors are being installed inside this thing. Again, this is like 3 feet long, not even 3 feet long, and it's got to put all this wiring inside. You can see this crazy mess. The CFD is hard, but this is a lot harder. Really takes a dedicated technician to do this very, very carefully. Here's the CFD image showing the location of the sensors, and all of these sensors really were selected very carefully. The location of the sensors were selected based on where the CFD predicts these heating streaks to be, and kind of where the best estimate is of where transition and how transition is going to occur. So there are thermocouples, there are high frequency pressure gauges, there are sort of standard Coolite pressure gauges. The purple things back here are high frequency heat flux gauges. So we really are going to get a lot of information about this very complicated flow field. And so hopefully we'll be able to unravel some of this and understand the physics underlying this flow field. Okay, so you can, next steps are to complete this analysis, and that hopefully is going to be done more or less by SciTech. And then we have to make these transition predictions. And I think really the big question is what the free stream state is and what the level of roughness is going to be. The model has been scanned, and so we're going to try to use the actual as scanned roughness state of the model. And then ultimately what we want to do, we're not going to be able to do this anytime soon, but to compute directly through the instability, through the secondary instability growth and through breakdown to turbulence. There's actually a second flight of this geometry. It's extended by about 50% or so. NASA's going to launch this one, and it's going to fly on a bigger booster. It's going to fly higher and then come back in more aggressive conditions so as to get higher Reynolds numbers and to get fully turbulent flow. So we're going to have, hopefully, if it all goes well, we'll have turbulence data on this configuration, again, for comparison with theory. Okay, thanks very much. I am happy to try to answer any questions.
Is the nose cone thing just falling when you're taking measurements, or does it have something behind it to guide it?
Yeah, okay, I didn't say that explicitly. So during this trajectory, what's shown here is just the nose, but it actually is a captive carry, so it's dragging with it the second stage of the booster, which has these big fins on it. And so that is really what kind of keeps it pointed down. You're right, any aerodynamicist would say, good luck with that if you're going to try to fly that without some kind of stabilization. So yeah, so that's right. Yeah, it's going to carry the second stage.
Thank you.
So, Graham, I have a question. So about the interaction with the surface, I guess this is a lower speed, so you don't need to do any of that. Besides, probably you need to change the emissivity coefficient when you change material in the tip.
For sure.
For sure.
Yeah.
And but at which regime you need to have some response from the material? I think right now you just need the conduction, no? But something a bit more complicated that involves chemical reaction and
yeah, it's all about speed, right? It's all about enthalpy.
16 or Mach?
No, and it's also the material properties, but there are catalytic effects for oxygen even at Mach 10 conditions.
So Mach 10 you would have to study chemical reaction. This is perfect gas.
All the analysis that we've done so far has been perfect gas. We do need to. I don't think there's going to be any oxygen dissociation, but there could be some vibrational excitation under these conditions. But again, it's only 7.3 or something like that. And you have this very small stagnation region. It's probably not going to be a big difference between vibrational excitation and just perfect gas. But we will look at that and verify that that's actually the case.
Can you go to slide 15, please?
In principle, yes. Hello? Oh, okay. Yes.
So I believe you promised explaining why n equals 5.5. Maybe I missed it. Can you explain that?
Yeah, right. So there's empiricism here. And okay, so remember, so let's think about the transition process. The boundary layer is going to go turbulent when the disturbances get to some amplitude, which we think is around 10%. The velocity disturbance is around 10% of the free stream velocity. So there's some critical amplitude. Now you have a disturbance field at a certain initial amplitude. Now that initial amplitude could be very low if you're in flight, or it could be quite high if you're in a conventional wind tunnel. And so So the n factor measures the log of that ratio. So if I'm in flight, I'm going to need a larger number of n factors in order to get to that critical amplitude. So by correlation, basically, by experience, we expect under Mach 6 and 7 type conditions that the NASA Langley facility and the Kubrick facility give about a critical n factor of 5 or 6, because they have a certain noise level. They're here, not down here. But in flight, we know by experience that probably that's more like an n factor of 15, because flight has such quiet conditions, very low amplitudes in the flow field.
And so are you measuring that initial amplitude in the wind chamber, or are you seeing from multiple tests that it's consistently around?
It's really the latter. I mean, there have been attempts to make that measurement, but all you can do is put a pitot gauge in there and and you just get noise. You don't really know what the structure of that noise is. It's really not very predictive. We are actually using on a MURI project with University of Colorado, we're making measurements in the upper atmosphere of turbulence levels and particulate levels to try to characterize, the transition's going to happen around 100,000 feet. What's the turbulence level up there? So that we will then have an amplitude that we can use to try to do a more amplitude-based transition prediction. But that's down the road.
All right, thank you.
So you showed all these different instability modes, and I was curious, I think that was the mixed mode or something.
Sure.
That did not propagate downstream, but there was a small transient region where it was actively suppressed, and then it reappeared again further down, and I was just curious as to why that might be the case.
Yeah. Well, this is pure speculation, but you see this region, these second modes are, this region is perpendicular to the flow velocity, right? It's not oblique. And now you see that it start to become oblique as you go downstream. So this is probably just noise, that there's amplification in the boundary layer, and we're just plotting one magnitude of the streamwise velocity perturbation. So really, if you were to plot a range of magnitudes of velocity perturbation, what you'd see is this disturbance dying out and then seeding, because it hasn't gone away completely, seeding a new disturbance. I think that's what's going on. And it's really not a second mode. It's not related to that at all. It's just that the residual noise and disturbances from that activate this disturbance. But yeah.
One more question. Andre, way up front.
Yes, sir.
Hold on. The microphone is on its way.
Thank you. So on this same slide, so in this case, you're advancing the linear dynamics under this stochastic forcing. Is that right?
That's right.
And I guess I'm just wondering, do you have access to the linear operator? I mean, could you look at the most receptive modes and kind of circumvent this process?
Exactly.
Okay.
Yes. So that is, you'll have to invite me back for another talk on that.
Yeah.
You'll probably have that working by then.
The assistant professor is the wrong tree to be barking up, but.
I'm working with Joe Nichols, Professor Joe Nichols at Minnesota, and basically we now can take the derivative of that flow field with respect to the state, and now we can apply all sorts of interesting linear stability or linear systems analysis methods to that Jacobian. And one of those is an input-output approach where we have this huge Jacobian that represents, how the flow field responds, and we can poke it at one place and measure the output, and we can take the output and project it back onto the input. And this is going to allow us to connect that particular disturbance to a particular forcing quantity. And that's what's going to be really exciting. Doing it on this geometry, we can do that in 1D, in 2D, we can do it in 3D to some degree. Doing it on this scale of grid is not there yet, but it's coming. It's just computation and just. It's not trivial, but that's what's coming next. Yeah, so that's a great question. Cool.
All right, I think for the sake of time, let's leave it there. Thanks.
Thanks a lot.